Close to my own intro. Okay, hello, I'm Martin. This is Tef. Tef's actually been flying with me. Was it fun?
A lot of fun.
Yeah, okay.
Scary as well.
Okay.
I would have been introducing it.
So, this is a talk about flying for free, hacking the atmosphere, you could think of it as well. The photo here is taken from a glider about 2 kilometers up above the clouds, as you can see. We're actually climbing at 2 meters per second. We don't have an engine. We started from about 300 meters. We went about 150 kilometers on this flight, and all the energy we used for that we stole from the atmosphere. So that's what this talk is about. Think of this as hacking the atmosphere. Birds have been doing this for millions of years. In fact, this hack is so old the dinosaurs were doing this, the pterosaurs. We've been doing it since about the 20s or 30s, and now in the last couple of years we've got unmanned aerial vehicles which are autonomously doing this by themselves. And what we're doing is exploiting moving air in the atmosphere in order to climb and to travel distances. In English we call that soaring. In German you have Segelflug, I think, sailing flight, which is quite a nice term for it, I think. Some figures: flights to over 50,000 feet, that's 15 kilometers up, done by Steve Fossett a few years ago before he died. Distances over 3,000 kilometers, again recently. But
can you put on the solution to 1024?
Is that stopping the video?
This means we can't capture the...
Okay, right, okay. Yeah, okay. Got that. Low, yeah, please. Is that going to... Yes, okay. Now, doing this, there's a lot of aerodynamics involved, there's a lot of factors that go into the design of the aircraft to make them optimal for doing this, but in terms of actually flying them, it's an information problem. We need to work out where the lift is, where we need to go, how to optimize our flight, and there's a whole load of data analysis that comes into doing that, modeling what the atmosphere is doing, predicting it. And increasingly, we're doing that not just in our heads, but with the help of electronics and software, both on board the aircraft and on the ground. So it's an interesting technical problem, which is why I thought you guys might be interested, and it's also a hell of a lot of fun, and it's cheaper than you might think. To learn to fly on gliders is really a fraction of the cost of doing it on powered aircraft, and you can also pick up old ones very cheap. You can own your aircraft for less than 1,500 euros. I can confirm that with some I saw advertised just before I left. So these are some of the aircraft that do this. So birds have been doing this for a long time. You've got older sailplanes like this, which are wooden construction. More modern ones are fiberglass and plastic, carbon fiber, some of them. Since then, people try to make simpler things, hang gliders, power gliders. They don't perform quite as well, but they're cheap, and I guess some people like them. This aircraft here, it's fairly typical of a large remote-controlled model glider, but this particular one is actually autonomous. It's a UAV, and that's Dan Edwards there, who's working on that at North Carolina State University. So to get these things in the air without an engine, a few ways to do it: either tow them up behind another aircraft, or just accelerate them to flying speed by attaching them to a cable hauled in by a winch on the ground. You go up quite steep to about 300, 600 meters. You can also just go off the top of a hill, either on foot, a hang glider or a power glider, or bungee launches for large gliders like these, where basically just very large elastic band. And then once we get up there, the main thing that we're trying to do is to exploit air in the atmosphere that is rising. We know that the atmosphere, there's air moving horizontally, that's the wind, but there's also a lot of vertical movement, and that's what we're primarily exploiting, although there's things we can do with the wind as well. So any glider has a sink rate. That is maybe 1 or 2 meters per second. So flying through still air, there probably isn't any vertical movement in here. It's coming down at 1 meters per second, but if it came into some air that was rising at, say, 2 meters per second, you add those and we're actually going to be climbing relative to the ground at 1 meter per second. Unfortunately, what goes up must come down somewhere else, and on average, all the vertical movement in the atmosphere has to add up to 0. So you'd think that that would cancel out and we'd end up with the same descending glide angle already, but if we can figure out where the lift is and fly in such a way that we spend more time there than in the sink, then we can actually gain even though the average is 0. Now, where that lift comes from can be a whole range of sources. There's 3 main ones. The simplest one to understand is just hill lift, where you've got the wind blowing onto a slope. There's force to rise up. The air above that is forced to rise above that as well, so it knocks on further up into the atmosphere. This is why you see paragliders, hang gliders, especially flying near hills because it's very strong lift. Thermals, which are bubbles of warm air that have been heated near the ground and then they're floating up through the atmosphere because they've got a higher temperature and so a lower density than the air around them. Most people, quite a few people are aware of this anyway. The one that people don't know so much about is wave, which is actually pretty much the most exciting. So this is a very large scale effect that happens after air is blown over hills or mountains, and it's gone over the mountain, it's had to rise a bit and come down the other side, and it gets very turbulent in what we call the lee, the downwind side of the hills, and this sort of forces the air to ride over that turbulence, and you often get this oscillation set up, and these waves can propagate a long way downwind and a long way up as well, and that's where the really high altitude flights come from, and also some of the really high speeds and high distances. So combining these different areas of lift from various sources, we can travel distances by just climbing in one area of lift, moving to another, descending as we go, but then climbing again, and you can extend this, and we routinely do, for hundreds of kilometers and sometimes thousands. Now, just staying up and wandering around to wherever the nearest lift is relatively easy. Going in a particular direction is harder, so as a challenge we set these tasks, basically a sequence of waypoints. Start here, try and fly to here, here and here, and on this one, as well as the straight lines that indicate the sort of task that's been set, the coloured line is indicating the flight path I actually took on this flight, and you can see where we've been circling in thermals and drifting with the wind, and then working across wind to come back, and then into wind coming home. The colours here are mapped to the altitude. So you can see here that we're climbing, going from green to blue, and then we descend again and climb again. I'll show you this one in 3D in a minute. So this leads to this, what I think is the heart of the problem here, is this sort of optimization situation where we are here and we want to get to some other point in the atmosphere without touching the ground in between, through a time-varying 3D vector field that we don't actually know any of the values of. Well, we know the value at our current position because we can work out whether we're climbing or descending, and we know the values just behind us. It still doesn't give us an awful lot to go on. So in order to do this effectively, we need to understand what the patterns out there are. So basically, it turns out that our atmosphere is a really, really bad random number generator, and it's got loads of pattern vulnerabilities that you can find and exploit. So this is, to give you a sort of visual impression of what that's about. This is part of a simulation from a weather model. It's about 50 kilometers aside, showing thermal bubbles in an area. And so we're trying to go from completely transparent air that we can see out there to a mental picture or a software picture of, where is this lift, what does it look like, how can I go from one bit of it to another. And so to do all this, we need to understand the weather that actually gives us a lift. A bit of video just to help picture what this is about. This is our glider just taking off on a winch launch. It's me waving it goodbye. Quite a steep climb. This aircraft's worth about €2,000. That's the winch hauling the cable in, and then as you rise up over the winch, just release the cable, turn away. This is over an airfield in Scotland called Portmoak, which is where I fly from most of the time, and we're quite fortunate we have this nice big hill that almost any wind direction we can get some lift off that, basically just by flying along near it like that and working our way upwards from there. And you can actually see how much the air is rising. The glider's climbing in that turn. You can actually do quite a lot of cross-country flying in certain areas just by purely hill lift, just working along ridges, get some height, jump over to another one. The Lake District in the UK is particularly good for this. Aerotow launching, just stay behind the tug. This is a glider thermaling, so it's circling, trying to stay tightly in an area of lift, a bubble that's maybe 400 or 500 meters wide. And that's me doing it. And just coming up, there's a view down there, somewhere in southern England. This is a variometer. It's an instrument basically telling you that you're going up or you're going down. There's 3 other gliders in the thermal above us. And you can do that right up to the base of the clouds, and then to get above that, often this is involving waves. So this is actually a view from in the wave at about, looks like about 12,000 feet maybe, so what, 3-4 kilometers. And you can actually see the waves in the shape of the clouds there. It's going up, down, across there. So, a little bit about the performance of these aircraft. So you may have learned in school the classic force diagram with lift, drag, weight and thrust. We don't have the thrust, so the forces have to balance out this way, and that's why when you fly a glider, it will come down at an angle. And you can see that that angle actually comes from the ratio between the lift and the drag. So these things were coming down at what, 3-4 to 1, something like that maybe? And that determines your glide range as a ratio of the start height. So that's 3 or 4 for a paper plane. We regularly get 30 to 50. That means we can start from 1 kilometre, fly for 30 kilometres. The record's at 72, that's this aircraft here called the Etta, 30-metre wingspan. Aspect ratio of the wings is over 50. Very long, very thin, very flexible. You actually see this thing pull up and it goes like that. Hang gliders are catching up, paragliders basically won't. It's not the only aspect of performance, because we're also interested in how slowly can we get the thing to come down, because if we're in lift, the rate of our climb is the rate the air is going up minus our sink rate. So that determines the minimum lift we can use. We need to be manoeuvrable to stay in a tight area of lift. That isn't. It takes blimmin' ages to make those wings turn. And we're also interested in the relationship of both the lift and drag to the speed. I'd say if you want performance on a budget, the nice thing about gliders as opposed to hang gliders and paragliders, which have a relatively limited lifespan, is these just last for decades. There's no engines, there's hardly any moving parts. So this one is designed in 1966. This particular one that we have is actually built out of spare parts of a couple of different ones. There's the figures. Glide ratio 33, fly for a kilometre from a wingspan or so. It'll come down at 0.7 meters per second at the minimum sink speed. And you can fly it up to 250 kilometers an hour. You have to kind of point at the ground a bit to do it, but it's good fun. It'll loop, it'll roll, it'll do all that good stuff. Older ones than that, you even get free. People haven't got time to look after them. So a little more about the performance. As I say, the lift and the drag are both related to the airspeed. So as you fly the aircraft faster by diving a bit or bring the stick back and fly slower, you change those and you change the sink rate. And if you plot that, you get these polar curves, what we call them, that are characteristic to the particular type of aircraft, and things like how much load it's carrying and whether its flaps are down or that sort of thing. And this gets involved in lots of calculations for working out what the optimal speed to fly is. So in still air, to get the best glide, the furthest distance from a given starting height, if you take a tangent from the origin here and plot it to where that meets that curve, that gives you the best glide speed. And if you're in lift or you're in sink or you've got headwind or tailwind or you've got ballast on board, these all shift that around and you get different optimal speeds. But half of it depends on what lift you expect to find when you get to the next climb. So optimizing this is all a bit complicated. Instruments we carry on board these things, that's the panel kit out in our glider. So altimeter, airspeed. There's two varios here, one electric, one mechanical. The electric one, the main advantage of that is it's got an audio feed out, so beep, 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 you're going up, and no, we're going down. Extra bits, artificial eyes, and so on. Radio is quite common. We fly with a parachute, just in case, never used one. We have oxygen on board for wave flying, because you get above about 3 kilometers, you start to need it. GPS, increasingly present. Flight loggers keep a record of your flight. You can do this on the PDA, but the official ones are tamper-proof black boxes that give you a cryptographically signed copy of what you did, and that's used for scoring competitions. But this is the really interesting thing that's just appeared in the last few years, is getting a PDA in the cockpit. And a little bit of flight logging there. So this is the same task I was showing you earlier, the triangle that you saw the 2D trace of. This is in 3D. This has come out of the flight logger, and so you can see we found a thermal. We're climbing. Oh, that's enough. We'll go over here, and that's how it works. And when you do a competition and you get maybe 30 or 40 aircraft all trying to fly the same task, you get this great bit the next day where you put all these traces together and you have what we call a maggot race, where you watch these things go around and try and it's interesting because you get to look at which pilot did better, and it's all strategic decisions. It's all effectively algorithmic. Who's got the best algorithm for navigating and finding the best lift, and consistently the same pilots come out on top. It's not just luck. The software running on these PDAs is all specialized stuff. There's been commercial products for this for some years. They're pretty much getting overtaken now by this one open source project, XCSAW. It's GPL'd, it's written in Microsoft stuff because Microsoft own the PDA market, unfortunately. But it gives you this sort of view. Again, this is actually replaying data from that task, so that's turning the same corner at the first leg. And this is telling me where the restricted airspace is, all the navigation information, the task, all sorts of numbers I might want to know, how much more height I've got to gain in order to be able to fly around the rest of the task, the dotted line for how far I can get to if I want to land, various airfields I could land at and what height I'd get to the map from here. It's really bringing down the workload and increasing the access to information to the pilot. The rest of the technology that gets involved is on the ground and is basically about weather forecasting. So this is basically all the old traditional ways of getting weather forecast information for soaring. Now we need to predict what the weather's going to do, because that helps us decide, do we want to go flying today at all? Is it worth it? If so, where should we go? What lift can we expect when we get there? How can we plan our flight? And so probably the first thing we look at on a given day is the synoptic chart like this. This is a pressure map on a large scale. We've got the whole of Western Europe here, showing us, and what the pressure is doing tells us what the wind is going to be doing. Here it's going to be flowing around the isobars like this. And these are fronts which are going to bring rain and stuff. So that tells you roughly what the air mass you're dealing with, what's going on is. This is a sounding. This is data from a weather balloon that's been sent up, taking a cross-section through the atmosphere, temperature, pressure, humidity, that sort of thing. And using this data, you can predict with reasonable accuracy what the thermals are going to do, what the trigger temperature needs to be, how hot it has to get for the thermal to start, how high the thermal is going to go, where the cloud base is going to be, how strong the lift is, that sort of thing. And then closer to the time, probably on the actual day of your flight, you can look at the satellite picture. It's going to tell you, here we can actually see some wave on this. And rainfall radar tells you where the rain is, and if that's coming towards you, you might want to fly to avoid it, go somewhere else. This all takes quite a lot of skill and experience to figure out what it means for the actual day in question, and it's all a bit big, low resolution. I mean, you've got the whole of Western Europe here. You've got high resolution on this, but it's not what we're interested in. These soundings, there's 15 of them, I think, taken daily in the UK, so that's to cover the whole country. So what's exciting, again, just very recently, is that we're now getting much higher resolution models, which you can actually just run yourself. So this is a program called RASP. It's basically a Perl script tying together a bunch of code that's come out of academia and various bits of freely available data. You can run these models on a Linux PC in a few hours at resolutions down to about 1 kilometer. And what you're doing there is you seed it with information again from those soundings and global forecast data as well and other observations. And so you get an initial estimated 3D state of the atmosphere over the whole area you're interested in forecasting for. And then the program cranks through all the fluid dynamics, the equations of motion, to work out what would actually happen. And by the time you've run that for some time steps, it reaches an equilibrium that pretty well, it seems, matches what actually happens. And then we can go and extract all the interesting parameters we actually want, like how strong are the thermals that we actually want to know to fly. And the data that's coming out of this, it's getting better and better, and it's pretty much revolutionizing some aspects of soaring. And as I say, at the moment, 3 to 4 hours to run this, but as the computational power goes up, what we're going to be able to do with this sort of stuff is going to get more exciting. All of this, you can get all the info on it and download it from the address there. And it'll give you rain, it will give you sun on the ground, wind speed, all the things that you're interested in, even if you're not a glider pilot. So, thermals, a little more about them. It's all come from solar heating, but the sun doesn't really heat the air very much by itself. What it does is it heats the ground. The heat just goes straight through the air. And then the air that's sitting near the ground is what actually heats up. And so you get a sort of bubble of air near the ground, and that wants to go up, but it's kind of lazy and it just sort of sits there until something actually gives it a bit of a push. And then once it's actually going, if the temperature and pressure profile in the air is right for it to keep going up, then it will. And again, you can predict that from the sounding information. The bubble will separate and rise, and as it rises, the pressure decreases, it expands and it cools. And once it gets cold enough, which will happen at a given layer that we call the cloud base, then the water vapor in it is going to condense and form a cloud, which is great because it says, look, there's a thermal here. Unfortunately, what it really says is, look, there's a thermal here that's almost finished. Do you want it to be back over there? But we'll come back to that. Well, this is a time-lapse video in which you can actually see this sort of thermal development happening. So each one of these cumulus clouds, there's some paragliders up playing with them there, is marking a thermal. Here's one you can see the thermal has just hit the cloud base, and it's gone boom, and it's formed that cloud. And the energy in these things is incredible. I mean, this is thousands and thousands of tons of air churning around. There's a huge, huge amount of energy in there to be tapped. It could go quite high. This is Norway last year. We were quite lucky with this trip. We arrived on the hottest June day they'd ever had, and the thermals went up to just over 3 kilometers. And to find these, we're largely relying on visual information. So the cloud's the most obvious one, but there isn't always a cloud, and the cloud doesn't necessarily mark where the thermal's starting. But it's a pretty good bet. So you see a cloud, go under it, you're going to get some lift. So we spend a lot of time just going from cloud to cloud. If we don't have a cloud, or if we're lower down and the clouds are marking where the thermals were, but not now, then we're looking for the points on the ground that are actually triggering the thermals. So this might be areas that heat up more because they've got a different surface, like a town with lots of tarmac and concrete. Or it might be if there's a wind, and you've got some warm air that's blown across the ground, and then it meets something cold, like a lake, and then that starts it going up. Or it hits a hill, and that starts it going up. And you often get the same thing, the same trigger point on the ground will trigger one thermal after another, and so you get a line of them in the sky, and you can work your way along that line with being in lift pretty much all the way. You can also see what the birds are doing. If there's a bird flying around, go join him, he's probably right. If you find one, he'll come and join you. They're quite good at that. They're not stupid. Same for other gliders. And if you're completely stuck, you can just fly a blind search. Find a straight line or a search pattern and wait till you find some lift and try and center in it. This picture here is a very, very, very obvious thermal trigger. It's a 4 gigawatt power station. And that's staring down the chimneys of it. But most of the energy going up in this thermal is not coming from the power station. It's coming. It's air that's warmed up, sitting on top of all this concrete and stuff, and in the surrounding area as well. But the updraft from this is allowing it to suck it up and bring cold air in underneath. Very often you go over that power station and the conditions aren't right for thermal to rise. You won't get any lift at all. It's not just the power station feeling that. That is no, that's Drax. So, having found one of these, you need to try and get in the strongest part of the lift. You're somewhere in the bubble. The middle is going to be strongest because what it's really doing is it's going like that. It's almost like a mushroom cloud, churning outwards, and the middle is the strongest. And so you're in the lift, you're flying around in circles, and somewhere there's the strongest part of this, and you want to get as close as possible to that. So it's actually a classic hill climbing problem, with all the attendant problems of finding local maxima when the core of the thermal is actually over there. And so, again, you need to have some sort of mental or software model of what the lift actually looks like. This diagram here is actually from Dan Edwards, who's doing the autonomous soaring stuff, and he's using a simple Gaussian distribution for the lift, assuming that's what the lift is, and then flying, matching his observations of what the lift he's finding on the path is, and then fitting that model to his observations and working out, okay, the core is over there, I'm going to go over there and climb. So yeah, NASA did this project in 2005. This is, again, autonomous soaring UAV. This one was the first one to sort of demonstrate that, yes, you could do this. It just fly in a straight line. There's some lift. Okay, let's assume it's a thermal. Let's try and center in it, and they get a few hundred meters climb out of it. And now this guy Dan Edwards is doing taking this further, and he's starting to do cross-country flights. So in October, he did this 97-kilometre flight that's, I think, beat a record or two. And here's a flight trace from it. It's just flown in a straight line. It's found some lift here. It didn't think it was good enough. It's found some more here. It's tried to centre in that. And it's wandered into another one and tried to centre in that. I don't think it's doing that well, actually. You want to be turning around here, turning around here. Those are very clearly the cause there. It's all moving downwind as well, because the bubble follows the wind. These are both very well documented. The NASA one, there's a paper on it that you can download there. Tells you pretty much everything you want to know if you want to build one of these. Any paparazzi guys in the room? Dan Edwards has a site there. Hill lift, I said a bit about it already. The thing to bear in mind is it has a knock-on effect going upwards, so the lift can work for a long way above the hilltop height. On this hill here at Port Moke, we routinely get to a couple of thousand feet above the actual top of the hill, which is then enough to go off to another hill somewhere else or whatever. Very, very predictable. Again, if you want to do this autonomously, all you need to do is have a terrain height map and to know what the wind speed is. And if you want to know what the wind speed is, just fly in a circle and watch the GPS drift. You don't need big hills. The Dutch have basically no hills. It hasn't stopped them. They just do it on the sand dunes on the beach. Wave. This is the good stuff. It doesn't happen everywhere, it doesn't happen all that often, but when it is good, it is very, very good. It goes high. 3 to 6 kilometres, that's 10 to 20,000 feet is common, routine at some sites. 15 kilometres, say the 50,000 foot record from Steve Fawcett, that was over the Andes in Argentina, is possible. And it goes a long way downwind. You can see it because where the air rises, just like with a thermal, the moisture in it condenses and it forms a cloud. And then as that air comes down, that cloud breaks up as the moisture evaporates again. So you get this line of cloud that's actually laid out perpendicular to the wind. You can see them on the satellite picture. Here the wind is coming this way, and the wave bars show up as ripples. And to exploit it, you just stay in the upwind part and stay the hell out of the downwind part, because it is going down just as fast. This can easily be 1,000 feet per minute or more. Again, time-lapse. This really illustrating the fact that the pattern is stationary. The air is moving through it very quickly. The wind speed at altitude is actually very high. And so although the cloud appears stationary, if you take a still photo of it, it's actually continually forming on one side, breaking off on the other side. And you want to be about here. And at which point you call your friend who's in the office and he hates you. That's over Scotland. You get these very complicated systems of one set of waves that's happening at one frequency and wavelength at one altitude, and another one that's going in a different direction at another altitude, and you have to try and jump from one to the other by waiting until they cross over and getting a climb. Or if you want to fly upwind or downwind, you've got to jump from one bar to another and go through that sink, which is where getting a good glide angle even at high speed is important. Again, stacks of wave. This is getting up to something like 19,000 feet over Scotland. And it very often sets up in the evening once the thermals have stopped, and so the ground heating's gone and they're not churning up the atmosphere anymore, because you want quite a smooth air for this. And so we often get these lovely sunsets up there amongst the wave bars. I mentioned these high-resolution forecasts. This is, to me, the most exciting thing that has come out of those, is we now have the resolution to see individual wave bars on the forecast. This is a 4-kilometer resolution plot from the RAS program for the Sierra Nevada. That's just over 200 kilometers that way, and so probably 600 down there. And this is a cross-section through the air at 500 millibars, so something like 20,000 feet. And it's showing the vertical velocity of the air. And so the red bits are going up, and the yellow bits not so much, and the green bits and blue bits are going down. And so it's taken its atmospheric state, and it's run it over its whole model that includes a high-resolution picture of the mountains and so on, and it said, right, it's going to do this. And sure enough, there's a satellite picture from the same day, and the agreement between these is incredible. You could have sent your UAV up and said, look, fly there, and there's the wave bar. Now, there's one guy who flies on the same side of us at Port Moat called John Williams, who's absolutely crazy, basically. And he's been sort of pushing the limits of what you can do with wave flying in Scotland. He's been making a lot of use of this, and he does a lot of wave flying, and he's found that this model really agrees with what he found. And so he said, well, let's take it outside the conditions we've tested. So he set himself a task with a turn point on an oil rig 20 kilometers off the coast. And he looked at the forecast and said, yep, the model says the wave bar carries out that far. And he went out 20 kilometers off the coast and found the oil rig and flew back. I don't have the photo, unfortunately, because it's not on the web. But yeah. So that's kind of where we are. We're still pushing the aerodynamics, we're still making the airplanes better, they're getting more expensive in the process as we're having to use fancy materials and all sorts. This means the old ones are getting cheaper, and what was the hot shit yesterday is now cheap. But fundamentally, most of what we're doing is about information, and so greater achievements are going to come from better information. So the things I see happening are going to be most interesting is just getting more and more weather data from more and more sensing. If you can put sensors on every aircraft in the sky, maybe, if you can do it cheap enough, you can get away doing it, even just all the gliders, then rather than just 15 sounding balloons from various places over the country, you've got a whole load of samples through various tracks through the atmosphere with which to improve that state for the models. Obviously, we're going to get more cores, we're going to get faster clocks. Well, maybe not going to get faster clocks anymore, but what currently takes us a few hours to run on a desktop machine was either going to be running on the PDA or at least in a larger box in the back of the cockpit, or just run it on the ground, getting into near real time and transmit the data up to the gliders. The UAV stuff is interesting because there's the potential to fly much smaller aircraft with greater maneuverability that can do things with areas of lift that are basically too small or too complex for us to exploit with anything that's built big enough to carry a person. So we may have things to learn from them. They've certainly got things to learn from us, because right now they can't look out there and say, right, there's a cloud, I'm going to go to that thermal, but no doubt that will happen as the computational power to do the machine vision for that gets easier to put onto the aircraft. But unfortunately, as with a lot of things, our biggest challenge at the moment is political. Increasing regulation, increasing costs of certification of aircraft and so on is making things awkward, and the amount of airspace that commercial air traffic is demanding and more regional airports opening up and expanding is reducing the amount of sky that we can use, basically. So if this strikes you as something interesting, I really encourage you to try it while you still can, because sometimes it seems like it's going to get killed off. if you do want to try it, the way it works is you have a flying club in an area that generally has an airfield and owns some of its own aircraft, including some that are used for training, and they'll have some instructors to teach you in those. The best way I could figure to give everyone a useful link, this is the link that's at the FAI, which is the international body for all air sports, to national gliding and also hang gliding and paragliding federations. Find your national one and they'll have a list of clubs. You can find one close to you. You join up, you go through basic training up to going solo, just learning to fly the aircraft, take off, land, all the usual. It's possible to get up to solo standard, at least in the UK, for £500 to £1,000, depending on whether you can get a cheap deal if you're in a university. A lot of universities have clubs, that sort of thing. Well, I've certainly seen sort of £1,000 fixed price to solo. A pound equals €1 pretty much at the moment, which is painful but true. Most people take about 40 or 50 flights to go solo. A lot of those are 2-minute flights just to deal with things like launch failures. And even before you get to that standard, there's plenty of opportunity to do all this interesting flying. There's no need for you to be a solo pilot to go and up in a 2-seater and do all this cross-country flying. But when you do want to do that, you just take some further action. It's an adventure, because taking off without an engine, you never quite know where you're going to land up. You always plan to come back to one airfield or another, but sometimes you get it wrong and you just have to pick a field and land. So then you get to meet the locals, who are always very interested to see, who's this guy who's just come and landed in our back garden. I think this is some British, aristocrat's back garden up here somewhere in Scotland. And then you have all the fun of trying to get the trailer out to where the glider is, which can be awkward country roads, and take it to bits and put it away, take it home, try again tomorrow. That was my worst. It wasn't even my glider, I borrowed it. And it's a wooden one, it's covered in fabric, and the fabric's doped, so the cows love to lick it. I landed here, and there was absolutely no human being in sight. It was clear right to the horizon. I just shouted, "Help!" as loud as I could, and no one came. And I was running round and round this thing in circles, trying to stop about 30 cows from trampling all over the wings, and eventually got the crew out and got it back, and spent the whole next morning wiping cow saliva off it. I've got a few minutes, so you get some bonus stuff. This is really interesting stuff that's just happened in the last couple of years. This is 2006. The problem with gliding as a spectator sport is it's really boring. You get to watch the aircraft all take off, and then they come back a few hours later, and that's it. So we've been trying to improve that with Grand Prix style races, where the scoring is simpler, everyone starts at the same time. And they threw a whole load of money into this. They did this in New Zealand, which is pretty much the best gliding anywhere. And they had a chase helicopter, they did live tracking of all the aircraft. They got the same people on board who did the animation and stuff for the sailing races. And it was absolutely awesome. You can get the whole thing on a DVD called Gladiators of the Sky. So that's just a clip I've taken out of it, but it's really worth a watch. I mentioned crazy stuff that you can do at smaller scales. So this is dynamic soaring, which is a different way of getting energy out of the atmosphere. So there doesn't need to be any rising air, there just needs to be a difference in wind speed. And we pretty much learnt this one off the Albatross here, because they're quite good at it, they do it all the time. So what's going on here is you've got wind that's changing with height. Usually the wind gets stronger with height, and so they do this over the ocean. So you've got some waves that have blown up, and then the wind's blowing over the waves, and behind the waves you're in the shadow from the wind, and the wind's a bit less. So what you can actually do here is, if you're flying in the slow air behind the wave, and then you suddenly climb up into the faster air, you've gained airspeed. As you've gained airspeed, you've got more lift, so you can pull up, change that kinetic energy you've built up against the wind into height. That gives you potential energy. And then you can turn around, dive back into the slow air. You suddenly, gain ground speed doing that, turn, come up, and repeat this. And they can go across the wind like this, they can stay in the same place, they can go between waves and go downwind. And there's been a tiny number of flights where, in really weird conditions, where like full-scale gliders have been able to do this. Not right near the sea, but sort of different, wind shear conditions. But model gliders have now got really good at it, at doing it behind hills like this. So these are completely unpowered, just things about this big. And this is the back side of the hill. The wind's coming from this side, and it's gone over the hill. And so the wind's strong up there and weak down here, and they're just doing the same thing. And the speeds they get into with these things are incredible. There's a record at 440 kilometers an hour now. And all the energy is free. All you can do is just throw it off the hill, and you can do this. This is real time. Yeah. So we've still got a lot to learn. There you go. That's it. Questions?
Is there any way to get up in the jet stream?
Steve Fossett was working on this before he died. I don't know if you know this story. Steve Fossett is the guy who did the solo round the world flight. He's done balloon flights, and then he crashed in a little Cessna or something a few months ago. It took a long time to find him. But he had this project called the Perlam project. And they were trying to break the glider world altitude record by using these sort of jet stream and very high altitude wave effects. They're trying it over New Zealand, they're trying it over Argentina, and eventually they got this 50,000 foot height record in Argentina. But he was talking about being able to go to 100,000 feet in the jet stream with a specially designed glider. So his calculations are probably good. Got that mic there.
Thank you. I got two questions. Tell us more about coming back after landing. And the second is, how big is the smallest glider possible?
The smallest glider possible that can, carry a human? The smallest glider that can carry a human, or? Okay, the smallest glider that can carry a human. Well, I mean, you can wear one of these wingsuit things, and you get a glide angle of 1:1. And there's a great video on YouTube of someone doing this and just going down a mountain that is about the same angle. So it depends what angle you want to be able to come down at. If you don't mind it being that angle, then it can be this big. If you want it to be more, then you need to start putting some wings on there. To answer your other question about coming back after...
Yeah, I thought about the handling of this thing.
Oh, okay. So the question's about handling the aircraft after landing. So I didn't stick a picture in actually because I couldn't find a good one to hand, but the wings come off. The wings, you can carry them with two people, so you just have the glider parked up, disconnect the pins, just a couple of big pins that hold the whole thing together, pull those out and take the wings out, and then the whole thing goes in the trailer with the fuselage in the middle and one wing on each side and the tailplane just shoved in somewhere. So yeah, it takes 20 minutes or so to put one together or take it apart again. Most of them just get kept in their trailers, dismantled, and when you want to fly them, you put them together because it's cheaper than having a hangar.
If you have an electrically powered plane that can glide well, is it possible to convert some of the energy Here, you gain from terminals into stored electrical energy for longer flights instead of just speed or altitude?
You could do, yeah. I mean, if you've already got a propeller, and you've already got a motor on there, a motor can work as a generator, so if you've gained a whole load of height, you just dive and take the energy that you get from spinning the propeller. I haven't heard of anyone doing that seriously, and I think the margins of energy that we're working with are generally quite small, so I don't know how effective that would be unless you had some really, really strong lift frequently to play with. Batteries are heavy. Well, it's interesting. I mean, we fly with a lead-acid battery about that big to power the electronics that we have on board, GPS and loggers and all that. And a couple of those will last you for 12-hour flight, no problem, and more. Electric-powered self-launching gliders are starting to appear. John Williams, who I mentioned, actually flies the first one of those that's come into the UK. It's called the Antares, and it's a 20-metre thing, and it's just got lithium polymer batteries in the wings, loads of them, and a few kilowatts of motor on it that just folds away.
Is this working? Yeah. It's sometimes said that man is not made for flying, so was there sometimes moments, or how often do these moments happen that remind you of this way of thinking? I mean, do you personally or other people that you know?
You get up there and you days like that, sitting up above the clouds, rubbish, we were meant to fly. If whoever's up there didn't want us to go to fly, want us to fly, wouldn't have given us brains, he wouldn't have given us vulnerabilities in this random number generator.
But how small do those radio-controlled gliders get?
You can make one as small as you can make. I mean, people make model aircraft down to tiny little scales, not usually as gliders, but you could do. But again, it's a case of glide angle. I'll come back briefly to the picture I had of the ETA and explain something about wingspans and glide angles. The reason this has really, really long wings, the ideal wing goes on forever. It doesn't have an end. If you test a wing in a wind tunnel, the ends go to the walls of the tunnel, and so there's no way for air to come off the end of the wing. It has to go over and get guided by the wing and down, and that's where you get the lift. But in reality, we have to actually have an end to the wings. But the less significant you can make the ends, and the more you can approximate the ideal infinite wing, the better the efficiency gets. And so for a given amount of lift you've got to generate to hold a couple of pilots up, then your wing loading's fixed, and to get close to that, you have to make the wing longer and longer and thinner, and use more and more expensive materials and constructions to do it. So that's why you have these very high aspect ratio wings, is to keep the tips as insignificant as possible. Also, the winglets here, these little bits that flip up, it is also just designed to reduce the effects that go on at the end that gives you the vortices off the wing, because that all the energy you spend twirling the air around on the ends of the wings is wasted its drag, and the airliners are copying this now.
You mentioned carrying a parachute. Wouldn't you expect by the time you realize you need it to be too low for it to be of actual use, and are there any other emergency measures available?
The main scenario in which parachutes gets used is mid-air collisions. We fly, you saw the video earlier with 3 gliders all close together in the same thermal. In a competition you can have 20, 30 gliders all in the same thermal. We always circle in the same direction to make sure it's easier to see what everyone's doing and so on. But we do spend a lot of time flying in close proximity, and very rarely mid-air collisions do happen. We have to do it because the lift is in small areas. So that's the main time that they get used, but it is very, very rare. aside from that, no, I mean the glider is your means of getting down, and the parachute is your backup. You are. The question was, other emergency measures. You are seeing on some newer aircraft fancier escape systems to get you out quicker. Not quite the full-on James Bond ejector seat, but close. And also some with parachute that you can deploy from the aircraft to recover the whole aircraft, slow its descent. But not very common as yet. One more?
How about doing this in the ocean?
That's an interesting question. How about doing this in the ocean? I don't know. The fluid dynamics are going to be the same principles, but it's a much thicker fluid. So all these dimensionalist numbers that get involved in the fluid dynamics, like the Reynolds number and so on, are going to be different. You have, obviously, ocean currents. I don't know how much vertical movement you get in the ocean. In theory, yes. I mean, the other thing I can mention is talking about doing this in different fluids. One of the reasons NASA was doing that project is they thought it might be interesting to do this on Mars, which has a quite different atmosphere and less gravity, so might be quite good.
Hi, you haven't talked a lot about traffic control, so do you have a radio to communicate with others, or how do you ensure that you don't collide, or don't go into an airspace that is preserved for public transport?
Yeah, use a map. So an air map is a normal map with all the areas of controlled airspace, danger zones, all the airfields, all the stuff you're interested in as an aircraft marked on it. And if you're flying more than a few miles from the site that you started at, you're supposed to take a map and a compass. And you keep track of your position, you have to navigate, that's one of the things you learn, and you avoid going into that airspace. Since we've got the PDAs and the moving maps, that's helped a lot, and that software, you program it in with all the 3D airspace information, and it will actually warn you. It will say, look, you're 1 kilometre from the edge of this airspace, and you say, oh, okay, thanks, some of it you can call up and get permission to go into, but it's a hassle because gliders present a sort of unusual situation to the flight controllers. It's like they expect something that's going to fly at this speed, at this level, and we don't do that. So mostly we just stay out of controlled airspace entirely, and it's part of navigation is avoiding that.
So you don't have a radio?
Most gliders have a radio, so you can use that to, if you want to enter some airspace, you can call the relevant unit and request it.
I've got time for a few more questions. I think only last question. One more? Anybody?
Michael, please, for the recordings.
Can you wait for the mic so we get the question on the...
Hi. What was the reason for the massive increase in restricted airspace that you were saying? You said it was political. Is it mainly commercial airlines or?
Yeah, I mean, in the UK at least, the government has decided a few years ago that air transport is incredibly important and needs to be subsidised and prioritised, and that the airlines can have pretty much what they want. And so domestic air traffic has increased. It's cheaper to fly from one part of the country to another than to take the train, which is crazy but true. And so you've got lots more smaller airports in areas that weren't previously really using air travel directly, opening or getting bigger and more traffic between them. and just more traffic between the bigger airports as well. And as the traffic levels increase, they feel they need to, the other thing that's going on is they want to burn less fuel. And so rather than flying up through some controlled airspace and then through an established airway and down to another airport that maybe isn't the optimal route, but it goes through controlled airspace that they know is not going to have anything else in it, they want to burn less fuel by just going straight from A to B, or at least closer to that. And that means airliners over a lot more of the sky than there would have been before when they were concentrated into corridors. Is that it?
I think that's all the time we've got.
Okay.
So I think
thanks very
Martin,
much for listening.
Thanks again to Martin. I'm sure we'll be outside to answer any other questions you might have. So thanks.